The views expressed in this interview are those of the individuals and do not reflect the official policy or position of the U.S. government, the Department of Defense, the U.S. Navy, or the Naval Postgraduate School. Welcome to the Trident Room, brewer of stout conversation, unfiltered and on tap. On today's episode, Trident Room host Luke Gorsky sits down with Dr. Jeff Haferman.
Hello and welcome to the Trident Room podcast. I'm Luke Gorsky, and today I'm joined by Dr. Jeff Haferman. Dr. Haferman is a director of research computing within the Information Technology and Communications Services Office, better known for all you NPS folks as ITACS, here at NPS. His team runs the Hamming and Grace supercomputers on campus, and they recently deployed the TMG Core EdgeBox computing platform for a 5-month evaluation period. We're going to be discussing supercomputing efforts here at NPS, as well as how supercomputing can be leveraged by the DoD as a whole. Dr. Haferman, thank you very much for joining me today, and welcome to the Trident Room podcast.
Thank you, Luke, for having me.
So before we dive into supercomputing and what's going on here at NPS, can you just give our listeners maybe a little bit of a background on you, how you ended up here in beautiful Monterey, California?
Sure. So my undergraduate degree was in mathematics from the University of Chicago, and then I actually worked for a while in Chicago at the Chicago Board of Trade, which it was a mathematical kind of background, and working at the Chicago Board of Trade, I got very interested in working with, this was a time where scientists were just starting to explore financial markets, and that motivated me to go back to school and really get a better understanding of computing, because I thought seeing physicists and engineers working in the financial markets, it was quite eye-opening in terms of what people could do with that kind of mathematical and computer background. So I decided to go back to school and get advanced degrees in mechanical engineering. So I did that at the University of Iowa. Went on to do a postdoc at NASA Goddard outside of Washington, D.C., and I was working in the area of what's called satellite remote sensing. So I think people at NPS may be familiar with that. It can be used for a variety of things, but the way that I was applying it at NASA was for weather forecasting. So really just kind of thing that you see on the television news, where every night they're showing, here's the satellite imagery. We have people here at NPS that are doing satellite remote sensing. That was kind of my background, and there was a job at Fleet Numerical, which is just down the road here in Monterey, and that's the Navy Weather Central.
Right. Mm-hmm.
So I had all this education. I didn't really know what I was going to do with it, but I got into the satellite remote sensing area, and I just happened to be looking at jobs for seeing what area can I get into with all this background. And Fleet Numerical was looking for people that had a background in satellite remote sensing. And I'd been through Monterey before, and I said, well, there's a job in an area that's not too bad to live in.
No,
and
not at all.
So that's back in that was 1997.
There we go. So you've been here for a while.
Almost a quarter century now in Monterey. And so that's where I started my career, 9 years at Fleet Numerical. Mm-hmm. And then in 2006 moved here to NPS. At that time, the provost and the CIO, so Leonard Ferrari was the provost at that time, and the late Dr. Christine Haska was the CIO, and they were looking for, they wanted to get supercomputing back at NPS. So NPS has kind of had an up and down history with supercomputing, going back to the 60s. One of the first supercomputers in the country was deployed at NPS, and it was designed by Seymour Cray. So NPS had that, and then it went away, and then a decade later got supercomputing again, and so it's kind of gone up and down and up and down. But decision was made back in the early part of 2000s, let's get supercomputing back at NPS. So they did a recruitment, and I had a background in that area, so I applied for it, and hired, and that's kind of how I got here.
Well, it's great that you're here, and it sounds like we're definitely on that upswing with supercomputing as it goes with here at NPS. So great foresight by some of the NPS faculty and staff back then to get it started now, so that we're in the position where we are now, where you guys are experimenting with a lot of new and interesting different applications for supercomputing. So kind of as we start breaking into that, I think that supercomputing is something that gets a lot of headlines, kind of a buzzword, things like that. What would, in the simplest terms, I'm a poli-sci kind of guy, so some of the more numbers nerdy stuff doesn't resonate as well with me. What's kind of a good tagline for supercomputing that you would say the general public can get?
Well, it's changed a little bit over the past few decades. It used to be at some point it was just you get a processor, a CPU, so everybody, whether you're poli-sci or whether it's your grandparents or parents. Sometimes it's our kids that are the wizards, but everybody's using computers and cell phones, and so it used to just be a supercomputer was something that you'd go out and buy, and it would have a very, very fast processor. It would have a faster processor than what you'd have for your home computer. That's still true to some extent, but nowadays it's more just buying lots of processors. So if you go out to Best Buy or Amazon or wherever you're buying your desktop, laptop computer from, people talk about cores. Oh, I have a quad-core computer, or I have 2 cores, or something like that. But it's usually just a single, what they call CPU, central processing unit, that you'll have in your desktop or laptop machine. Our supercomputer here at NPS, and any place where they talk about supercomputing, sometimes they use the word high-performance computing, or the acronym HPC. That's synonymous, really. Supercomputing, high-performance computing, same thing. But what we're doing nowadays is we're just taking the same type of processors, for the most part, that you have in your home or school system, and we're just getting lots of those. So our Hamming supercomputer here, for example, we've got somewhere in the neighborhood of 4,000 cores.
So is that kind of 4,000 computers? I mean, if you looked at an average home computer, there's about 4,000 computers hooked up to each other.
Yeah, you might have a dual core computer or a quad core computer at home. So it's maybe, let's say that you have a quad core computer, and so it might be like 1,000 of those linked together, and so they're all linked together by networking cables, and so that's part of the trick of it too. So you could really think about it as, okay, let's just go out and buy 1,000 laptops, and then just hook them all together, and try to make those laptops communicate with one another. So and people have done that. They've actually gone out and bought laptops and linked them together.
Yeah, I think
we have servers that we link together.
Yeah, I remember some story. I think it was the Air Force that bought like 1,000 PS3s something like that,
exactly,
and threw them all
right.
together.
Yep.
I don't remember how long ago. The
Yeah,
last decade or so.
It wasn't that long ago. It was maybe a decade ago, where the Air Force did exactly that. They took PlayStations, PS3s, and linked them together. We did something similar. We only had like 3 or 4 of them, but we did that for a project where we had some students from the Naval Academy that wanted to learn about supercomputing, and it was about a decade ago. And we went out and bought PlayStations for that very very thing. So it was an internship project. So it can be done with whatever you've got available. The trick is getting those computers to talk to each other and sort of cooperate and solve what we call like difficult or big problems. An example would be weather forecasting is one that's sort of, again, at Fleet Numerical. They're using supercomputers. National Weather Service uses supercomputers because it does require so much processing power.
Yeah, so I think, yeah, whenever I've doing a little background research on before our podcast here today, I think a lot of the examples that I read about did talk about weather forecasting. Kind of my understanding there's a reason it's really useful in weather casting is just because the extremely huge numbers of variables that then affect the other variables, and so you need these really high level performance computers to do that. What are some other applications beyond that, or what are you guys using it beyond maybe weather forecasting here at NPS?
Yeah, sure. Great question. So really, it's almost any of our departments that are doing any kind of computing will come to us. So it's primarily GCs, which is our Graduate School of Engineering and Applied Sciences. So those are what I'll call our hard sciences, our physics, mathematics, electrical engineering, mechanical engineering, computer engineering. Look at those schools. I'll give some examples of what they do, but then GSWAS, so Graduate School of Operation and Information Sciences, so operations research, computer science, information sciences, they use it. We also have our, I lose track now of what the business school is called. Graduate School of Defense Management
Sure.
Systems now. So we'll have to make sure we get that one right, but it's changed. So we have some researchers there that are using it. So and I know you're in national security affairs. We haven't had in a while. We haven't had anybody from there come directly to us, but I know we've had some people in national security affairs that have been working with the information sciences department. There's been some collaboration that's gone on there, and I know we've had them working with us over the years. So I'll give some examples in all those different areas, because that's one of the things that's made what I do and what my team does. It's made it a little bit challenging because we don't have just one customer. We have customers from all these departments, and they all have different applications. So in GCs, that is more of our traditional weather forecasting in the meteorology department. The oceanography department is doing things like oceanographic modeling, so they're maybe looking at like modeling of wave heights, or polar ice prediction is another thing that they're doing.
For the Intel guy here, sound propagation to find some submarines.
There you go. That is being done as well. So acoustic modeling, there's a lot of acoustic modeling, and that's going on now. And I'll give this is a really interesting interdisciplinary thing that's going on. Is we have people in the oceanography department that are working with people in the physics department, that are working with people in the computer science department, that are working with MBARI, which is the Monterey Bay Aquarium Research Institute, which is up in Moss Landing. So that's sort of the academic side of the Monterey Bay Aquarium. So they have some, and this is all public domain info. They've got, if you were to go out and do a web search, you can find out about this, but they have sensors deployed in the Monterey Bay, and they're listening for marine mammals. They have these acoustic monitoring stations set up, and they're listening for whales is an example, but any kind of sound that's in the bay. Sometimes it's I know they've done things that are even I think that fishermen can use explosive devices to get seals out of the area. We're trying to fish here, and so I know they have to be licensed to do that. But I know that that's one thing that can,
so they can monitor to make sure the fishermen are all on the up and up whenever they're doing those types of things.
And see how often this happens. And so I know I have to know a little bit about all the type of work. I don't get into it deep, but I know enough about it so I can try to accommodate the work that they're doing. But so this is a really interesting example where we've got several researchers. We've got an outside entity, MBARI, Monterey Bay Aquarium Research Institute because they've deployed these sensors. Then we've got researchers here that are trying to apply their skill set to it. So the oceanography researchers they've done some models of the acoustic modeling. The physicists they've done things with signal analysis. So they do all of they can take these they can actually just look at the data sets and they can actually analyze, here's a little spike. So they have models that can say, okay, when we see a little spike, something happened there. That's an event that we need to look at. But there's so much of this data, terabytes and terabytes of data, that they have to figure out, signal versus noise.
Right.
When are we looking at noise? When do we have a signal? Then we've got our computer science people who are doing artificial intelligence, which they're trying to apply models to it. So again, there's so much data there that we've got the physicists trying to pull out the signal, and then the computer scientists trying to put AI techniques to it to say, okay, well, this is a whale, or this is an explosion, or this is a boat going by. So we've got all these people that are working on this problem together. So it's kind of that's just everything coming together. All kinds of researchers working on one particular problem.
Yeah, so I guess then my kind of follow-up to that would be, when exactly or how does the supercomputing actually integrate into that? Is it kind of, I don't know, stovepiped is probably not even kind of the right word to use, but are like the oceanography guys running their model and then with the use of the supercomputer, right? Like they go and, is the model being built by the supercomputer or aided? What exactly?
So yeah, great question. What typically happens, and there's a number of moving pieces here, but first of all, there's like the just the data piece and the data acquisition. So they've got those sensors, and I don't know a lot about what happens between the sensor gathering the data and then transmitting it here. To me, that's sort of a black box. But at some point, we've got a data feed. So the data is just coming in, and it's just like if you're downloading information,
a movie or song
downloading
or a
movie,
podcast.
Yep, to your computer. That's kind of what we're doing. They've got a feed out there, and we're just receiving that data, and we're downloading it onto the supercomputer. So we've got these data sets are tens of terabytes, or maybe in the 100 terabyte range. So it's a lot of data, and so there's just that data set that's there, and then all of these different researchers. So whether the physicist will have they'll have their own set of programs that they're running on it and doing their analysis. The oceanographers have their programs that they're running. The computer scientists will have their programs. So they've all kind of, sometimes they use commercial code, sometimes they build their own, and the physicists might run their program on it, the oceanographer will run theirs, the computer scientists will run theirs, and they all then will communicate. Maybe they get together and will write a program together. But typically, again, what makes my job and the job of my team challenging is we have to make sure that the programs that all these people are using will actually run on the supercomputer. And sometimes they come to us and say, hey, I've got this program, I'm trying to run it, and it doesn't work. It's just like, it's very similar to a lot of times if you get a new computer and a program that you used to run on your old computer doesn't run anymore, or you upgrade and it doesn't run. It's really the same thing. It's just that we've got dozens of customers, so we have to support them, and if there's a program that isn't working, we have to look into, is it user error? Is it our system? Is it the computer code? So it's it's very similar in a lot of ways to what just a consumer faces when they're dealing with a new program and troubleshooting, and where is the problem. And we have the same thing. It's just on a different scale.
Oh, yeah.
That's really what it comes down to.
So you got a lot of people with like programming background working for you that are trying to troubleshoot this, or is that?
Yeah, usually it's the end user that does the programming for the most part. It'll be that physicist or that oceanographer or the computer science, and the folks that work on my team, we call them system administrators, but they might have a special expertise in storage or networking, or sometimes it is programming. So it's kind of have to have some knowledge in all of those areas.
So then, as this data is coming in from these sensors out in Monterey Bay, how much is this like live analysis done versus you store up 10 terabytes of data and then you run these algorithms on it?
Yeah.
Is it?
Yeah, great question. So they tend to be not. We get the data, fairly, I'll call it fresh, but it isn't like instantaneous live. But they tend to be analyzing them retrospectively. So
Right.
we get the data and it's there, and they can analyze it, and then they can go back and analyze it again and again and again and over and over. But I think every researcher is different. Some of our researchers are analyzing what I'll call like historical data, but with the eye toward being able to analyze real-time data.
Okay.
And so, I'll give another kind of to shift gears and talk about some of the other applications. Yeah. But there's similarity in a lot of this. It's just the underlying data set. So we have this acoustic work that's going on from the Monterey Bay. I think the goal would be to be able to analyze it in real time. This artificial intelligence, boom, there's a signal, and we'd have a program running that would say, okay, that's a whale, or that's an explosion, or that's a ship, and be able to do it in real time. And in order to do that, you have to really look at historical data and go through it and create these models.
So to kind of dig on that for a minute. So as they're running all these different models and simulations on the data that comes in, supercomputing resources are limited, right? So is the eventual goal, or is there a potential for, once they figured out, okay, we figured out how all these things work, how this code works, these programs work together, so now we don't need as much processing power as we did when we were designing things? Is that?
Yeah.
Does that happen?
Yeah, absolutely. So especially now I can kind of jump into like the area of artificial intelligence a little bit. The idea, just kind of artificial intelligence 101, if you've ever gone on to, Google is a common one, but doing like an image search. So if you show Google a photo, what it does is it will attempt to tell you what that's a photo. So if you show it a photo of a bird, it might say eagle. This is an eagle. So the way that usually happens in artificial intelligence, there's something done that's called training. So you're actually taking a computer and you're training it to recognize it. So what happens is, let's say I've got 1,000 pictures of, or whatever number, 10,000, 100,000 pictures of birds, and I've identified each one. Okay, this is an eagle, this is a robin, this is a cardinal. So the computer models actually go through and they look at each image like pixel by pixel by pixel, and they use what are called, algorithms and curve fitting and neural networks, et cetera. All of these things are kind of buzzwords, but the computers actually are given an image and say, this is an eagle, this is a cardinal, and so you give the computer thousands and thousands of these images, and the training process, usually researchers will do something like, okay, we've got 1,000 pictures of an eagle or of birds, and we're going to use 80% of them to train the model with. And we're going to withhold 20%. So the computer has never seen this 20%. So we're going to train using this 80%. We're going to withhold this 20%. We know what everything is here, and we're going to see how well we train the model by taking, after we train it, we're going to take the images that we withheld and see how accurately does the computer get it right.
Mm-hmm.
And that's what Google does, just with their images, and our researchers are doing the same type of thing here. That's how that's AI 101, how that works.
So that whole kind of training process requires the processing capabilities that you see in supercomputers.
That requires that training process is extremely compute intensive and requires a lot of our computing resources. Once the model is trained, then it's actually pretty quick. That's why you can go to Google and you can upload an image and it'll come back almost instantaneously. So that actually that's the classification process. That can be done with very little resources. It's done on Google servers. But you upload an image and Google says, "Yep, that's a blah blah blah." So we have researchers here that are doing that same type of thing, but they're doing it with data sets that are of interest to the DoD. So in this case, the acoustics in the bay are of interest for there's a number of reasons, but one reason is we want to keep ships away from marine mammals. There's been or we don't want to be
running into them.
Yeah.
Thanks for joining us in the Trident Room. For more information about today's guests and topics, please visit the show notes. The Trident Room has been brought to you by the Naval Postgraduate School Alumni Association and Foundation. For questions, comments, and suggestions, please email us at tridentroompodcasthost@nps.edu and find us online at nps.edu/Trident Room